Hi, I'm Jeff Bier with the Embedded Vision Alliance, and I'm here today with Bruce Flinchbaugh from Texas Instruments. Welcome, Bruce. Thanks for joining me today.
Thank you.
So really excited to talk to you, Bruce, because you have just such a long history in computer vision and embedded vision. Before we get into some of the things you're working on now, maybe you could start by telling us a little bit about how you got started in the field.
Okay. I got hooked as a graduate student a long time ago in the 1970s. Began prototyping some systems and software using cameras at the time, which were not very easy to use, but it was quite exciting, and I got into it. Then at Texas Instruments began to try to focus on how we, many years later, began to focus on how we could make money using vision technology. And one of the key turning points was when the Berlin Wall fell in 1989. I was managing our image understanding branch, working for defense applications in computer vision. But the Berlin Wall fell, and I sensed that things would change. And defense industry, so as a research manager at TI, I basically sort of strategized what could we focus on that would be commercially and industrially important, because just sort of assuming that the defense market will sort of go away. It took 10 years for Texas Instruments before the defense market was sold, but business was sold. So I picked two areas. I'm quite proud of this. It was quite, I don't know, it's just lucky strategy maybe, but I picked video surveillance, and I picked intelligent transportation. What could we do with cameras and computer vision to make the world a safer place with both surveillance and security, and for automotive applications, so infrastructure. Of those two, I had a very small research group, so we focused on the easier one, which is video surveillance. We didn't need to have cars and cameras out there mobile. Throughout the 90s, we focused on video surveillance and pioneered a lot of what's known today as video analytics. By the end of the 90s, we built our first DSP camera. It was a network camera, one DSP doing everything. We had some video analytics in there, tracking people, recognizing events, and streaming video. It was still too early for the market, but now 10 years after that, in the year 2000, we're happy to say we've got substantial business now for video surveillance and a very strong group of vision engineers working in this field. That's quickly how I got here.
Great. So what is your group focused on today?
Our research group is focused on both automotive vision and video surveillance. We primarily work closely with our businesses to make sure our products have the right computing power and instructions to enable those applications.
Very interesting. So in surveillance, are you talking about intelligence inside the camera or somewhere else?
Okay, inside the camera, definitely. So what we've seen over the last 10 years, I regard as a revolution that came out of the digital camera and digital video industries. So it was mostly consumer, right, where digital cameras 10, 15 years ago really were very low volume products. But from the late 90s to the early 2000s, an example is in the year 2000, 2001, both HP and Kodak came out with their first digital still cameras that were completely powered by a programmable DSP. That was not for vision, that was for image quality, right? So other things that happened were just a couple years later, smart camera phones became very high volume. In fact, within a year, they became the highest volume digital camera on the face of the planet. And those two things together drove a tremendous amount of development, and all of them programmable. But even though they weren't being used for vision, today those products and many, many derivatives with different peripherals are available for vision applications. And so that's the kind of platform that we have. And then for video surveillance, we've even taken it to the next level where we have a system on a chip which integrates the video analytics, and we have many, many options for programmable processors for customers to develop their own vision applications.
Really interesting. So you were really there at the birth of embedded vision. So you mentioned using DSP in digital still cameras, kind of a precursor to smart surveillance cameras.
Absolutely.
Today, the chips that TI is making for smart surveillance cameras, are they pure DSP processors, or are there other kinds of processing elements in those chips?
For digital still cameras?
No, for surveillance, for video surveillance and other embedded vision applications.
So let's look at network cameras in particular for video surveillance. Network cameras have become the only way to get high definition video in surveillance, and that's basically driven the industry from the analog cameras to digital. So these cameras typically now have a system on a chip, which is doing all the image processing to form a beautiful high-resolution image, also compressing the HD image to typically H.264, so that it can be shipped out with minimal bit rate over the network. So that's sort of the bread and butter of today's network cameras. Because our processors, at least the ones that we make, also have programmable processors in there, which are not completely consumed by the video processing. That leaves headroom for video analytics to be added into some of our systems. And then the video coding itself is an interesting story, because what started as embedded software doing video coding back in the late 90s through the early 2000s, the Moore's law, in a sense, began to slow down, and the clock rates leveled off for embedded processors, but video requirements kept going up. So the video coding for HD has actually transformed itself from software to hardware accelerators. So it's been standardized and to achieve the high bit rates, high bandwidth requirements. So we have a combination of accelerators in there for video compression that are pretty much all hardware now in the state-of-the-art cameras, which leaves the programmable processors more or less completely available for analytics and applications.
Are those the same accelerators as used in the OMAP chips for smartphones?
Some of them are. So TI, we have a variety of many different chips with different combinations of peripherals. One of the key workhorses that we've used for vision a lot is called the C6000 family of cores. And some of those chips are in network camera platforms, some are in automotive vision applications, and a version of those chips are in some of the smartphone processors too. So a typical OMAP chip will have ARM, now multi-core ARM in there, but also have a DSP in there for some of these things.
And the DSP is supplemented also with additional more specialized accelerators?
There are some. So in the video analytics camera product, we have a special coprocessor for some more vision type things. The traditional one, though, is actually in the image pipeline. So when these multi-megapixel images hit the system, they're not ready for prime time. The images that come off a color sensor are Bier images, that we call them raw images, which actually don't look pretty. They have to have substantial processing. And to process 2 megapixels for HD at that video rate requires other hardware accelerators that are in there for image pipe. And there's other programmable processors in there for image processing, where they're very close to the image pipe. And of course, for next generation, we have new programmable processors working.
So would it be fair to say that a sort of typical architecture then for an SoC in one of these embedded vision applications would have an ARM CPU for, let's say, networking functions, a DSP processor for video analytics and some video processing, and then additional more specialized engines to handle the image sort of image improvement front end and perhaps compression as well?
Exactly.
So that sounds kind of complicated. From a user point of view, compared to just a DSP, single-core DSP processor, single-core embedded CPU, how do you make that kind of a chip usable?
Yep, that's a good question. Of course, in the smartphone market, if we take that extreme, there's not only multiple heterogeneous cores in a system like that, but people who produce smartphone processors are managing millions of lines of software. Right? So typically, my understanding is 5, 6, 7 million lines of software all together in a smartphone. And it's not just one processor. Some of those lines are in different processors. So I think it's fair to say that there's no one person on the face of the earth who understands all of that. So if you're off to build a smartphone, you're probably a major company who has the resources to do all that. But at the other end of the spectrum, you, as anybody, can access the same processor in the form of, for example, like the Beagle board, where TI invested a lot of money to make not only the software open source, but the board itself open source for customers to play and prototype. And so now, yes, but back to your question as far as the software goes, that you have the extremes of smartphone complexity versus, okay, here's a low-cost chip, a low-cost open source board. You're free to do whatever you want. Right? So, people typically get started with the ARM, with Linux on that platform, and then it's only the sky's the limit of how much they learn or how much of that chip they learn how to use.
And can they get access? If I go buy a Beagle board today and I port my own custom vision applications onto it, first on the ARM core, and I don't get the throughput I want, then the progression would be to move things onto the DSP and move things onto the various accelerators attached to the DSP. Does a typical user buying a BeagleBoard have access to all of that, down and dirty specialized hardware, or is that just for the Nokias of the world?
No, the access is there in the BeagleBoard system. Learning to use it is probably the learning curve there. There was I shouldn't mention probably who it is, but one customer out there, open source, using the BeagleBoard, actually produced a stereo vision application running very efficiently on the C6 kind of thing without TI involvement kind of thing. But it's possible. It's a question of how much effort they put into it.
So sticking with this idea of specialized accelerators kind of helping out the more general processor for a minute, I think it's easy to see why like video compression winds up in a specialized coprocessor because it's standardized. Everybody's running H.264.
Yep.
But the vision processing, whether you're doing stereo vision or optical flow or object tracking, generally speaking, it seems like everyone has their own algorithm and their own way of doing things. So that doesn't seem quite as amenable to putting into dedicated hardware. Do you agree with that?
I agree completely. It's a very fragmented from an applications point of view, and definitely fragmented from algorithms point of view, because we find that everybody wants to do it their own way. They've got their own secret sauce, their own proprietary algorithms, and that's always meant programmability.
So, hence the combination of fixed function and programmable elements. So, where do you see the challenges for customers today, for equipment manufacturers who are dreaming up cool new computer vision applications and algorithms on a desktop workstation, C code, MATLAB, or what have you, and then want to create a small, low-power, inexpensive implementation? What is that hard, and if so, what makes it hard?
It's not easy, but yes, we do it all the time internally, and many people who build embedded products do that. So in our labs, the way we typically work with getting something new prototype, we start with data collection and ground ourselves in what the real problems are that we have to solve for a particular application. And then we're typically on a PC using a combination of MATLAB, C code that we write, sometimes OpenCV functions, to prototype some capability and understand what it takes to really solve that problem. And then once we got the functionality understood, what the algorithms are, then we look at, okay, how can we get this running in the embedded platform? And of course, after you've done that a few times, it's easier after you've gone over the first learning curve. But, what we do next is typically look at using some of our highly accelerated libraries, like we have a library called ImageLib, another one called VLib. You can use some of those kernels which are already optimized if some of those are typically relevant. And then we optimize, we can profile and figure out where the bottlenecks are, and then we can optimize other parts of the system to run efficiently or as fast as needed on the DSP. And if we run into a wall where the processor doesn't have enough MIPS, then we go back to rethink at the prototyping level, because we might simply, the constraints of the application might not allow to have 2 or 3 of these processors, or maybe if you just have to have one. We find you can do a lot without resorting to multiple processors. So it's a balancing act.
So do you find that it is typically the processor MIPS that are the most precious resource, the thing that has to be most carefully optimized for, or is it memory size, memory bandwidth?
It's all of that. So to get the full entitlement of using the DSP, you have to be able to optimize for the core, but then the other part of it is the data movement, right? To get the data moving in efficiently. We have very good DMA frameworks to be able to exploit the automatic transfer. We call it hiding the I.O. so that the processor can be computing all the time, and basically the I.O. is happening for free at the same time concurrently while you're working on it. It wasn't always like that in DSP. Back in the 90s, I mentioned that we were working on video analytics, talking with many customers in the surveillance industry, and almost to a T, everybody would complain that, hey, there's no efficient way to get video into your DSP. Your DSP is great, but you have no way to get the bits in. And we end up spending most of the cycles of the C6 just to get the bits in, and then we have not much time left over to do the processing.
Right.
And we listen, and so the whole Da Vinci line of processors has sometimes camera, CMOS image or sensor interface directly on the chip, and also digital video ports so that an A to D for an analog video decoder can be connected directly to the chip. and the data, most importantly on chip, once it's inside the DSP, can be streamed directly to memory, so the DSP doesn't use any cycles to get the video in. So that was a lesson we learned 10 years ago, and then now it's millions and millions, even hundreds of millions of systems out there use these digital video interfaces to get the bits in and free up the DSP.
Now, do you find that whether it's TI doing the work or customers, is it common to bring a set of algorithms, from the workstation prototype into the embedded environment and find that you're just not going to fit, and for that reason go back and rethink the algorithms? All
right, so I'll start with my branch, which I understand really well. I've got some expert optimizers in my lab. And once they've gone through the process of learning how to optimize for the C6, for example, the next time they develop a prototype, they already have a good sense of what's viable and what's not. So at the prototyping phase, while they're evaluating different algorithms, they can fundamentally reject entire approaches because they know that it wouldn't fit well. Mm-hmm. That's the second time around, the third time around. The first time around, it's just you just have to learn and develop a sense. And so there's different processors. Each one of them have different capabilities, different limitations, and at some point you have to invest the learning curve to develop that product. If you're not concerned about low cost, low power, small form factor, then maybe you don't need to go embedded kind of thing, and maybe mm-hmm. some products you don't need to worry about that if you're happy living with a higher cost system, or even what would be closer to a supercomputer if you have a high-end PC with several other accelerator cards and stuff.
Right,
hundreds of watts. And
DARPA Grand Challenge cars where the whole back of the vehicle is filled with racks of equipment.
Yeah, that's cool, and it's important to the world to learn how to prototype those things, but then if it's going to be lower cost, higher volume, you got to figure out how to shrink that stuff. Mm-hmm. And that's what we tend to look at for embedded vision applications.
Very cool. So you mentioned back in the 90s thinking about transportation and surveillance applications, and those have certainly turned out to be important ones for embedded vision. What other applications are you thinking about now? You were right before, so I'm thinking you got better than average odds of being right again.
Well, it's really exciting. So there's a whole bunch of areas that I'm excited about. One is it's more generic, but it's the area of three-dimensional imaging. Mm-hmm. All right, so there's traditional 3D imaging for measuring shape of objects was a class of approaches known as structured light, where you shine light, patterned light, or different arrangements of light, and knowing the geometry of the projector and the camera relationship, you can form three-dimensional images or measure how far away things are. Of course, there's another approach, stereo vision, to do that. And there's a more recent technology, optical time of flight, where it's a light and a camera, except this time the light is being controlled and pulsed at a very high rate of modulation, and it's effectively measuring the speed of light, how fast, how light bounces off of surfaces to form a three-dimensional image. So that's one whole area that's taking off. Digital signage is pretty cool. There's millions of digital signs out there today in places like McDonald's and other stores and transportation stations. The exciting thing there, we've seen some customers developing digital signage cameras that you just mount the camera up on top of the digital sign, and it's automatically estimating how many people are in the scene, counting the people, and keeping track of demographics, like how old are the people, and what's their gender, how many men are standing in front of the display, which is very valuable from an advertising point of view, because you can change the advertisement to fit the audience that's in front, mm-hmm. just like we do on a PC when we click through different ads. So digital signage and the whole camera to keep track of what kind of market is standing in front of the sign is a growing area. One of my long-standing interests is what I call home monitoring. All right, so there's an Archerfish camera out there that has video analytics. I view that as the first and sort of best example of video analytics in the home. There's lots of other ways that can go. Imagine situational awareness for your house. So you're driving home, you pull out your smartphone and ask for what's the situational awareness of my home. And you've got cameras around your house, and they've been tracking everything that moves. And they may not be able to see everything, but if they saw something go into the bushes, an hour before, and it never came out, watching everything, then you might get an alert saying, we think somebody's standing inside your bushes by your garage door, something like that. So you could have, a new form of home situational awareness outside, similar things inside. Another big area is known as business intelligence, where retail stores, there's opportunities for marketing and improving business and customer satisfaction by cameras in retail stores. Simple one would be, there's a long line of people waiting at the checkout. Let's automatically dispatch other employees to go staff the registers so we can shorten that line. There's 3 people standing at the deli counter and there's only 1 person working. Let's dispatch somebody else to go help out at the deli counter. There's lots of things for vision.
I recently ran into a couple of companies that are doing vision systems that determine someone's emotional state from video of their face. So I can imagine applying that to the business intelligence.
Yeah.
The restaurant branch manager gets evaluated by how happy his customers are, as well as other more traditional factors. Yeah, lots of really interesting potential applications. What do you see as the technical challenges? What are the technical things that companies like TI need to do and your customers need to do in order to accelerate the pace of making those kinds of products a reality?
That's a good question. From a TI-centric point of view, we're most concerned with making sure our processors have the right kinds of operations and the right kind of performance to enable whatever those applications are, and these future things we can talk about. But TI is really not the company to answer all those questions, right? We're there to help, but we really rely on customers that have the bright ideas and the vision experts to go off and break through those barriers and solve those technical challenges. Some of them, like one thing that distinguishes broad classes of applications, is whether the camera is moving or whether the camera is stationary. So one of the reasons that video surveillance systems have been able to produce fairly advanced capabilities is because the cameras are on the wall and they're not going anywhere, right? They're fixed. A very boring job of watching this same area for the rest of the camera's life it's going to be watching. So there's all sorts of opportunities to take advantage of the fact that it's not moving. At the other extreme would be maybe a handheld camera in a smartphone, or stereo cameras or whatever, maybe 4 cameras in a smart camera phone, where as long as the person's holding it, we know it's never going to be stationary. So a lot of those techniques that have been developed for video surveillance are frankly not even applicable in this other kind of environment. So you need other things, and that's one of the long-standing challenges. There are some computer vision methods to deal with moving cameras and be able to solve for that, and there are other things which nobody's figured out how to do. So that would be a nice area for a lot of research to figure out how to always maintain awareness of what's happening, even though the camera's moving, not that rigid reference point.
Back in reminds me of the early days of audio and telecom digital signal processing, when TI really did quite a bit to educate engineers about, okay, you've learned the theory in school, here's how an FFT works, here's how the true decoder works, but here's the additional important piece of how to get it implemented efficiently, for an embedded system. Do you see TI playing a similar role in embedded vision? There's people coming out of school that really understand the algorithms and the history of different approaches to different vision problems, but the practical aspects of how to get it implemented efficiently is not necessarily really learned in school.
Yeah, that's still a challenge. And so one of my recommendations is, if somebody wants to do this, is to go to school, get a master's degree where you work in a vision lab to develop that maturity. Some of these vision problems were very hard. And to get over so I mentioned I got hooked on it in graduate school, but my very first projects were, I would call, sophomoric. I was a grad student, but I still felt like a sophomore because I was excited, but I was coming up with simple solutions to simple problems. And when you start to solve the harder problems, that's when you can run into a wall very quickly. A simple example might be, it works fine in an indoor environment against a white wall, with a white wall as a background. But if you take it outdoors with trees in the background and sunlight shining and cloud shadows moving over top, the same technique that worked in that simple environment might totally fail. So getting over that learning curve, there's really no exception for the learning. But there's other ways you can do that, right? So there's a lot of smart people in the world, and not everybody wants to go back to school. So if you're not still a student, then the other way is you find some other way to learn. Actually, I think the Embedded Vision Alliance and the Embedded Vision Academy that we're forming is going to be a valuable thing in that regard, to help people become more mature at vision applications without necessarily going back to real school.
Good. Very good. Well, it's been a real pleasure talking with you today, Bruce. Thanks so much for taking the time to talk with us.
You're welcome.
Please come back to www.embedded-vision.com, where you'll find lots of interesting interviews, video tutorials, technical articles, and discussion forums.